Hello Chem 1B, this is Chapter 17, Lecture Video 2, and we're going to continue talking about buffer solutions. So, if we look at this weak acid equilibrium here, right, we have HX, some unknown weak acid, is reacting with water, forming H3O+, and the conjugate base. This is a Ka equilibrium. What is the equilibrium constant expression for this reaction? As we know, it's products over reactants, so we have Ka is equal to our products over the one reactant we care about, in this case, HX. Now, let's rearrange this expression and solve it for H3O+, right? Because most of the time we want pH, right? Well, if I do that, I get that H3O+ is equal to Ka times HX over X minus, right? This is just me multiplying by the inverse of X minus over HX here to get H3O+ on its own. Now, why is this important? Well, let's think about the consequences of this equation. If we have some value y over some value x here for hx and x minus for their concentrations, when this ratio is equal to 1, our H3O+ concentration is equal to Ka. Now, it turns out that as we get really close to this ratio of 1, to get further away from it, it's a lot harder. This is when the best buffer is achieved, when both HX concentration and X minus are equal to one another. Because at this point, it's a lot harder to change your H3O+ concentration, therefore keeping pH relatively constant. Because if I add strong acid, it will decrease, our X minus here. But since these two are equal, that change is not going to be as big of a deal. Whereas if they're really far apart, a little change here will change our whole ratio here that we're multiplying by Ka dramatically. So this is when the best buffer is achieved, when we have equal concentrations of our weak acid and its conjugate base. This is when we have the largest, what we call buffer capacity, generally. So if that's the case though, right, if we have HX and X minus equal to each other, whatever they are, let's say it's 0.5 molar over 0.5 molar like we used in the last video, well, this cancels. These cancel out. And we get H3O+ concentration equal to Ka. Well, how do we get pH from that? Well, we take the negative log of both sides, right? So of this, and then, negative log of that. Well, what's the negative log of H3O+? Well, that's equal to pH. What's the negative log of Ka? Hey, that's equal to pKa, like we talked about before. So when we have like a buffer where we have equal concentrations of both HX and X minus, we know that pH is equal to pKa. Let's continue on. We're going to actually derive an equation known as the Henderson-Hasselbalch equation here. Let's take the negative log of both sides of this equation. If we do that, we get the negative log of H3O+. Hey, well, negative log of H3O+, that's just pH. We also get the negative log of Ka times this whole bit. We can actually simplify that a little bit using some log rules, right? When we multiply two things, that's the same thing as adding them. So like individually, so if I take the log of this and the log of this and I add them, that's the same thing as this expression. And again, the negative kind of carries over here. So negative log of this, that's pH. Hey, negative log of this, that's pKa. And then for whatever reason, they like plus signs better here. So if we want to make this a plus, we just need to flip these two according to a log rule, and that's what I'm going to do. That gives us this expression, which again is really just pH is equal to pKa plus, all that. This is known as the Henderson-Hasselbalch equation. I don't know. I think that name is so fun to say for some reason, but whatever. Which is basically going to state that pH is equal to pKa plus the log of your conjugate base concentration over your weak acid concentration. This equation only works for buffers. There are also some other limitations here, but calculating pH using this equation is so much easier than calculating it using ice tables. And so it's super handy. This allows for the quick calculation of pH of a buffer as long as we know these initial concentrations. That's one of the cool things about this equation is implicitly when we're using the Henderson-Hasselbalch equation, we're using the 5% rule, which means we're assuming that these two concentrations aren't changing very much, and therefore we can use their initials right in the equation. We're given for those. That's what we got. Now you need to know this equation inside and out, right? So if I ask you, hey, what's the pKa if the pH is this and this concentration are this, right? You should be able to solve for pKa or Ka, right? Once you have pKa, you should be able to get Ka. I could also ask, hey, if I know the pKa is some value, the pH is some value, or I want the pH to be some value, what's x minus if hx is this, right? Or any other variable in this equation given the other ones. So let's look at the Henderson-Hasselbalch rule or equation because it has some limitations. The first and major one is that it only works for buffers. You cannot use the Henderson-Hasselbalch equation if you do not have a buffer present in the solution. This is so important. And it's also so important to be able to recognize whether or not you have a buffer. The second limitation here is that you can only use the Henderson-Hasselbalch equation when you can also use the 5% rule. So we're looking at equilibriums that have constants that are less than usually 10 to the negative 4. So if your Ka value is 10 to the negative 4 or smaller, for sure, probably going to be fine using the Henderson-Hasselbalch equation. Or 10 to the negative 3 or less generally. The equation won't work when your Ka is larger than about 10 to the negative 3 or when we have a significantly larger concentration of Ha to A minus. This statement here is basically saying not a buffer, right? Because if you don't have significant concentrations of both of these, then you don't have a buffer. Also, if your Kb is larger than 10 to the negative 3, or when these two are significantly different from each other, again, this is basically saying not a buffer. These are when our equation just will not work. In these cases, we can still solve the problem. It just means you got to do an ice table. And you're probably going to need to use the quadratic. Okay. So let's talk a little bit about buffer capacity. Buffer capacity is a measure of how much strong acid or strong base can be neutralized before the pH begins to change significantly or appreciably. Generally, we state that any buffer can still be present as long as we're plus or minus 1 pH from the pKa, right? So let's say my pKa is 3.74. Then my buffer range is basically 2.74 to 4.74. This is where I have a buffer present in that pH range. Now, how long it takes to get from one to the other is really dependent on another component. So one, we can select buffers because different buffers are present, right? We could use a buffer with one weak acid and its conjugate or a different weak acid and its conjugate, and they all generally have different pKa's, which means they have different buffer ranges that are more suited to them. Now, the way we select a buffer is we select a pKa that's near the pH that we want to buffer at, right? Let's say I want to keep my solution's pH at 3.74. Great. Well, I should use formic acid as my buffer pair and formate because that pKa is very near the pH I want to stay whatever it is. If that wasn't the case, if I wanted the pH to be stable at 8 point something, well, I'm not using formic acid because its Ka is way too far away from that. The second thing is capacity is really determined on the concentrations of the weak acid and the conjugate base, right? The more, the better, right? In other words, if I had 0.50 molar formic acid, right, CHO2, and 0.50 molar NaCHO2, this is a good buffer. But if I had a buffer solution made up of 1.5 molar HCHO2 and 1.5 molar NaCHO2, well, this is going to have the larger buffer capacity because the concentrations of our weak acid and weak base are higher. The higher your initial concentrations of those two, the more your buffer capacity will be. All right. Again, the pH of the buffer, though, is determined either using the Henderson-Hasselbalch equation or, an ice table. In either case, we're going to be using the concentrations of both the weak acid and its conjugate base and the Ka of the acid to calculate our pH. So let's do a calculation. We're going to do it two ways. We're going to do a calculation using an ice table. And then we'll do that same calculation, but using Henderson-Hasselbalch. This is just to prove how much simpler the equation is, right? So let's say we have a 0.12 molar benzoic acid solution, and at the same time we have 0.2 molar sodium benzoate. Our Ka of benzoic acid is 6.3 times 10 to the negative 5. Now, this is a buffer solution, and I know that based on the acid naming system. If you remember that ATE turns into IC when we name acids, this is benzoate. And hey, look, I got benzoate. These must be conjugates of each other then, because the difference between benzoate and benzoic acid is probably a hydrogen, which would mean conjugates of one another. So we can tell by the naming system. We're also told in the problem that we have a buffer. So there's that too. But I didn't need to say that. So let's say we have an ice box. All right, we're going to solve it using the ice table method. We know our initial concentrations of benzoic acid. That's this. You could have just written HA if you wanted. I don't really care. We also know we don't care about water because it's pure liquid. We know our H3O plus concentration must be 0 initially, and we're told that our initial benzoate concentration is 0.2 molar. We can fill out our change row and add the initial and change to get our equilibrium row. And we can set all of this equal to our Ka, right? At this point, we can definitely use the 5% rule and solve for x, right? And if we solve for x, we get that x, which is equal to our H3O plus concentration, is equal to 3.78 times 10 to the negative 5. I'm covering up some stuff just because I want to get this all done in one shot here. Well, this is my equal to my H3O plus concentration. I can take the negative log of that to get my pH, and I get my pH of the solution as 4.42. Now, that's kind of a lot of work in comparison to the Henderson-Hasselbalch method of solving this problem, right? So if we're going to use the Henderson-Hasselbalch equation, we know it looks like this, right? How do I get pKa? Well, I have Ka, and I know that negative log of Ka is equal to pKa. So if I take the negative log of 6.3 times 10 to the negative 5, I get 4.2. And so I did this, and that got me this. And I know my initial concentration of conjugate base is 0.2 molar, so I put that there. And I know my initial concentration of weak acid is 0.12 molar, so I put that there. At this point, I plug into my calculator, hit enter, I get 4.42. And that's the whole problem. So you can see how much simpler it is to use the Henderson-Hasselbalch equation than solving the ice table. This is definitely a shortcut. It only works when we have a buffer, and when we can use the 5% rule. In this case, both are true. So let's do one last problem here. We want to calculate the pH of a solution that has a concentration of 0.543 molar acetic acid and 0.236 molar sodium acetate. Now, I didn't tell you this in the problem other than at the top here. This is a buffer, and we know it because it has acetic acid and acetate both present. So I'm going to use Henderson-Hasselbalch equation here. pH is equal to pKa plus the log of x minus over hx. In this case, this is C2H3O2 minus, and this is HC2H3O2. Respectively, these are our weak base and weak acid. So I need to take the negative log of 1.8 times 10 to the negative 5, and if you get that, the pKa here is equal to 4.74. So my pH is going to be equal to 4.74 plus the log of my weak base concentration, this guy, 0.236 molar, over my weak acid concentration, this one, 0.543 molar. And that's it. And if we do this calculation out, it gets us that the pH here is going to be equal to 4.38. And we're done. Okay, so if you have any questions, let me know, and I will happily answer them via email or in our discussion sessions.